recording. I have two versions. One is on Brewingcast, which is on Canvas, Media Gallery, or the Brewingcast page. The other is on YouTube. So do you have access to my recording? Raise your hand if you don't. Okay, judging by the decreased participation number, I think lots of people have access to my recording, which is good. That's the first one. Second one, midterm announcement. I made an additional midterm announcement. I'm sorry for the confusion. I can't securely get the lecture room I want in our class time. So our final decision is we'll follow the undergrad office arrangement to have the night midterm exams. On the exam day, I will still be here for like question and answering. Your TA will probably also be here. So that day in lecture will be a Q&A or a review session before the exam. It's like ask me any questions, we'll help you out. All right, the third thing is we have office hour. Our first office hour is tomorrow in my office, which is Young Hall 3077. It's also posted in the syllabus. So if you're interested in participating, I'm highly encouraged. We'll see how many people turns out. If we don't have enough room, I might want to move it to a bigger conference room. But I'll see how many people show up tomorrow, and we'll see. And tomorrow I might, if I am late for the office hour because of my other appointments, my TA will be there to help you out until I show up. All right, so that's all the administrative stuff in 2 minutes. Any questions? All right, so for anything that's updated, we'll keep it posted on the Canvas announcement. That's one of the most efficient way for me to get the announcement to everybody in class. Okay, so today we'll start talking about chemical bonds. Before we do that, just a quick review on what we covered last lecture, which is first thing, we discussed electronic structure like atomic orbitals, and atomic orbitals are actually electronic wave function of hydrogen atoms. So from today, you'll see me draw like s orbitals and p atomic orbitals, and these orbitals may start to interact with each other. So if you're not familiar with that topic, I highly recommend you go back, review our textbook, review your previous note, and just get yourself familiar in drawing those atomic orbitals. And then the second thing, last week, we were talking about electron configuration. Like, again, from today, I'll start to talk about electron configuration like you know it. For example, I would just point to fluorine and say, like, oh, fluorine has electron configuration of helium 2s2, 2p5. So, like, if you're not familiar with that topic, again, review it to get yourself familiarized it. And the third thing, again, at the end of our last lecture, we were talking about the molecular structure and different type of formula that gives you the 3D information of a molecule. So I forgot to bring a molecular kit, but I did today. So for example, this one, we have 4 carbon atoms, right? So each black one is a carbon atom, each white one is a hydrogen atom. And all these single ones, you can have free rotation. So that's why I highly recommend you get one of these molecular kits so you can get familiar playing around with it. Also, we'll be using the wedge and dash notation where we'll draw the molecule. So for example, for this molecule, if we draw it on paper, like if I put all 4 carbon atoms on the same plane, then I'll have something like this, right? And then you'll have this red one pointing there, and then the green one pointing down. So red. And the unshown one, we have the hydrogen that's pointing away. 3, 4, and I have 1 extra hydrogen for mysterious reasons, which is not good. Anyhow, so get your molecular kit and start playing around with it and get an idea about what the 3-dimensional structure of a molecule looks like. We'll come back to it when we talk about stereochemistry. But for now, we'll start drawing the bond length formula. Like the hydrogen is being hidden in that bond length formula. And then each point here is a carbon atom. All right, so that's our review. Any questions on these review topics? Hopefully not. Okay, and now we're talking about today's lecture. We'll be talking about two different lectures. We're spending two lectures on bonding theory, or in the other words, the purpose of our today's lecture and our Friday lecture is to get you an idea about what a chemical bond is. So these are all theories. I would use that very famous notation. It's essentially all models are wrong, but they're very useful. Like in the classical bonding theory, for example, the classical bonding theory are treating our nuclei as just positively charged point charge, and electrons are negative point charge, which is not physically correct because using quantum mechanics, we know that electrons are actually not just a single particle, it is a wave, it is an electronic wave. But thinking about the electrons and nuclei as point charges in the classical bonding theory can be very helpful in understanding the chemical bond to get an idea about what that chemical bond is and how the electron densities are localized. So we'll start with classical bonding theory. Although it's not 100% correct, it's super useful in organic chemistry. So before we actually talk about chemical bond, again, electron negativity is a concept we use a lot in organic chemistry, especially when we're talking about classical bonding theory, because in classical bonding theory, we're treating the particles as just point charges, right? So now the question becomes, where are these point charges more closely located? So that boils down to the electron negativity of the atom of interest. So for example, when we talk about electron negative atom, they attract electron more strongly. So examples of electron negative atom are centralized on the top right corner. So one way to remember it is fluorine being the most electron negative atom. It attracts electron most strongly. And then the electron positive atoms are like basically your alkali metals and everything that's on the bottom left corner of the periodic table. So the way to quickly think about it is electron negative atom wants electron. Electron positive atom wants to give away its electron. And if we're talking about the trend of electron negativity throughout the table, again, the best way to think about it is just pinpoint that fluorine as your most electron negative atom, and the trend goes diagonally. All right. So that's just a quick review on our electron negativity. And then in classical bonding theory, we have two different types of chemical bond. You'll hear ionic bonding and covalent bonding a lot. We'll quickly touch upon the ionic bonds, and then we'll move on talking about covalent bonds because that's more applicable in organic chemistry. And again, if you feel you don't have time to write everything down, you don't have to. Remember, I post all my annotated notes. So just pay attention to what we're talking about. Try to think through the concept, not to copy everything down from the slides. All right, first thing, ionic bonds. So ionic bonds are typically formed between atoms of very different electron negativity difference. So in ionic bond, if it is a pure ionic bond, we're saying there is a total electron transfer. If we use sodium chloride formation from the neutral sodium and neutral chlorine, we're forming sodium plus, which is a cation, and chlorine minus, which is an anion. So this is, again, a quick practice in writing out the electron configuration. So sodium has neon, and then 3s1. Chlorine, that's neon, 3s2, 3p5, so as their neutral element atom. After the charge transfer in the sodium cation, it's losing its one electron and reach its noble gas configuration of just neon. Likewise, in the chlorine case, when it gains an electron to form a chloride anion, what we're getting is neon, 3p2, 3s2, I'm sorry. 3s2, 3p6, which is equivalent to the electron configuration of argon. So in both cases, the sodium plus and chloride minus has the noble gas configuration. So that's as much as we're going to be talking about in ionic bonding, because it's less applicable in organic chemistry. We'll touch a little bit on it. So you still need to know in ionic bonding, full charge transfer, and that's about it. All right. So now we're ready to talk about covalent bonds, which is one of the most important concepts in organic chemistry. Like in methane, your carbon and your hydrogen forms covalent bonds because they're atoms of similar electron negativity. If you look at the periodic table, right, we say in organic chemistry, we're basically focusing on carbon, nitrogen, oxygen, hydrogen, and etc. So those are all elements with very similar electron negativity, and naturally they form covalent bonds. So the idea of covalent bond is slightly different from the ionic bond, where we're talking about entire charge transfer from an electron positive atom to an electron negative atom. When we're talking about covalent bonds, what we're having are electron pairs that's being shared in between the atoms. To take it a little bit deeper, remember when we were talking about the classical bonding theory, we're treating the nuclei as positively charged point charges, the electrons as negatively charged point charges. So if you recall Coulomb's law, which means when you put two point charges of the same charge, of the same sign, they will repel each other, right? So the idea here is the positively charged hydrogen atom nuclei will repel each other. So the plus E here, that's the charge of the hydrogen atom nuclei. We're using H2 as an example here. So without the electron pair sharing, the nuclei will repel each other. So these are demonstrating that blue line. That's the electrostatic repulsion. But in this case, the reason in classical bonding theory that we still have chemical bond, we still have H2 as a stable molecule, is that we have electron pairs that's being shared in between the atom. So these shared electrons will act as glue. So the way to think about it is these shared electrons will glue the atoms together. Or if we look at these purple arrows, so that's the electrostatic attractive force between the nuclei to the electron. So the electron in between the atom is attractive to both nuclei and holding the molecule together in the classical bonding theory. So since we're talking about hydrogen atom, so both hydrogen atoms have the same electron negativity. So naturally, this is just a pure covalent bond that is nonpolar. So when we say the term nonpolar, what we are saying is the electron is being shared evenly. It's right in the middle of the two nuclei. Alternatively, again, we're making chemical bonds with atoms with different kinds of atoms. So if we're having atoms with different electron negativity, for example, hydrogen and fluorine, remember fluorine is our most electron negative atom, it attracts electron more strongly comparing to hydrogen. So HF is an example of a highly polarized covalent bond. So the idea is the same, right? We have the hydrogen nuclei, we have the fluorine nuclei, and without the electron pair, they repel each other. But now with the electron in between the two nuclei, it glues the two atoms together. But now because fluorine attracts electron more strongly, we say that electron density or electron is being shared unevenly, leading to a polar covalent bond. All right, so when we're talking about polar covalent bonds, what we're saying is you have atoms of different electron negativity, and atoms of different electron negativity pulls the electron density differently. The more electron negative atom, like fluorine, will pull electron density strongly to itself and forming an uneven distribution of the electron pair. And that's what we say when we have a polar covalent bond. You can also describe the polar covalent bond by drawing the dipole moment. So if we have, again, HF, so in this case, the hydrogen is the relative electron positive atom in this pair, where fluorine is the relative electron negative atom. So because fluorine pulls electron more strongly to itself, the electron pair is going to be more localized towards the fluorine, or in the other words, if we're just looking at the electron, the fluorine will have a partial negative charge because the electron is more tilted towards the fluorine atom. And as a consequence, our hydrogen will have a partial positive charge. So with that in hand, you can draw the direction of this molecular dipole moment. So that's pointing towards hydrogen to fluorine. So I'm just showing here a linear molecule. So again, as a quick callback, you learned the VS-EPR theory before. To use the VS-EPR to determine the molecular geometry, right? So if you have a trigonoplanar or a tetrahedral molecule, you can also have molecular geometries that's having the molecular dipole moment build up differently. So again, it's a quick callback. If you are not familiar with the VS-EPR, the valence shell repulsion theory, I highly recommend you go back and review it, as we will start talking about polarity of the entire molecule. All right, so that's the end of this quick review on the classical bonding theory. Let's see if we have any questions before we move on. Okay, sounds good. So now we're coming to everybody's favorite topic, which is Lewis dot diagram. Again, Lewis dot diagram is not a perfect model. It has its, well, we always sometimes say it doesn't work. It doesn't 100% correctly describe the chemical bond, but it's super useful in organic chemistry. Or, I mean, it might be to an extent for everything in this class, Lewis dot diagram might be, well, 80% of the time it's going to be efficient. So, few things about the Lewis dot diagram. First thing, valency. So valency tells you the number of unpaired electron or the number of covalent bond an atom can form. So here, remember, again, we're treating the electrons as just point charges. So the unpaired electron in quantum mechanics has a different definition. So we'll just leave that aside and just, again, draw back to the 15th century and imagine electrons as point charges. So we'll use the period 2 elements as an example and to assign valency to these elements so you get an idea about how many covalent bonds this atom can potentially form. Let's say the monovalent means it has one unpaired electron. So it's either lithium, which only have one, or chlorine. So you have 3 of them paired up and just one of them singly occupied. And then we go down the periodic table along the group to beryllium, which has 2, and then oxygen, likewise. You have 2 unpaired electrons or divalent. Boron is trivalent, it has 3 electrons around it. And nitrogen, you have 1 that's paired up, and the other 3 are singly occupied. Then carbon is tetravalent, it can form 4 bonds. So never form 5 bonds with carbon atom, just not possible. All right. And again, just as a quick reminder, in quantum mechanics or electron configuration, when we say unpaired electron, it has a different meaning. It means like spin up and spin down. So that's a different concept. Don't mix up yourself's mind. Second thing about Lewis dot diagram is now we know what's the maximum number of covalent bond an atom can form by just looking at its valency, or in the other words, look at which group that element is in. Group 1, And group 7 are your monovalent, group 2 and group 6 are your divalent, and etc. The second thing is called the octet rule. So what it said is hydrogen wants 2 electrons, and the p block elements want 8 electrons. Since we're doing organic chemistry here, we'll leave the transition metal and d block elements away. Or if we put that octet rule into a formula that you can use, what we're saying is using the formula here, we can derive or we can calculate the number of shared electron pairs in that molecule or number of covalent bonds in that molecule by applying the equation here. What we have is 1/2 first, and then 2 electrons for each hydrogen, and 8 electrons for each p block atoms. That's carbon, oxygen, silicon, phosphorus, sulfur, etc. Or these, we can call it the octet fantasy. So that's the ideal world these atoms want. And then we minus it with the number of electrons available. So that's the reality. So when we're counting the number of electrons available, you want to keep in mind that charges need to take consideration. If your molecule has a total +1 charge, you need to -1 from your total electrons available, etc. So that's the octet rule. Now let's just do an example. I mean, just looking at the equation doesn't make any sense. We can do a quick example and see how that applies. NH3. I know lots of you can just draw NH3 Lewis-Dot diagram, just write on the paper, but let's do it the long way and see how we're gonna use the octet rule one step at a way. So first thing, we use the octet rule to derive the total number of covalent bonds. So this number of covalent bonds will equal to 1/2 times, we have 3 hydrogen. Each want 2 electrons, plus 1 p block atom, which want 8 electrons. And minus, so these are my fantasy, and minus the electron that is available. So in nitrogen, it's trivalent. It's in group 5. We have 5 valence electrons available to make chemical bonds. And we have 3 electrons coming from the hydrogen. So these are my reality. And doing the calculation, we get a total of 3. Or what that tells us is we have 3 covalent bonds. And now we're ready to draw our Lewis-Dot diagram. So NH3 Lewis-Dot diagram, we're putting the most electron positive atom. We'll put nitrogen in the middle. I mean, hydrogen is never in the middle. Then we have a total of 3 covalent bonds. And we have a lone pair on nitrogen. Or if you, again, as a quick reminder, if you remember the VSEPR theory, this is going to be a trigonal pyramidal geometry. So again, this is the VSEPR review. All right. We can also describe double bonds and triple bonds using using the Lewis-Dot diagram. So when we look at double bonds and triple bonds, that means you have 2 or 3 pairs of electrons that's being shared. So again, let's use N2 as an example. So we'll apply the octet rule. So number of covalent bonds equals to 1/2 times, we have 2 p block element, 2 times 8, minus the reality, which is 2 times 5. So that gives us 3. So we have a total of 3 covalent bonds in the nitrogen or N2 molecule. So naturally, we can draw it as the N2 molecule here. And here we have 2 lone pair on each. We have 1 lone pair on each nitrogen. And then in the middle, we have the triple bond, or 3 pairs of shared electrons. All right. So far we've been dealing with just neutral molecule, and they're nice and happy. We don't have like unbalanced charge. And now we're ready to move on to talk about formal charge. So that's the last topic of Lewis dot diagram. So when we say formal charge, so here's a quick equation to calculate it. You don't have to use it once you're familiar, but I mean, it's sort of nice. So to calculate the formal charge, you need the number of valence electron on that specific atom minus the number of lone pair electron, and then minus 1/2 of your bonding electron. So we'll use carbon monoxide, which is a classic example of formal charge and Lewis dot diagram. And let's see how to draw the Lewis dot diagram for carbon monoxide. Again, the first thing first, we always do the octet rule first. We have 1/2 times 8 times 2, because we have 2 p block atom, minus 4 from carbon, 6 from oxygen. So we end up with 3. It means we have a triple bond in carbon monoxide. So let's draw the Lewis dot diagram. We have carbon triple bonded to oxygen. We want them to have octets of electron, or 8 electrons with it. So both carbon and oxygen will have a lone pair surrounding it. So now there is a problem. We need to calculate formal charge on the carbon and oxygen here. If we look at carbon first, when we're calculating the formal charge of carbon, so that's number of valence electrons, so we have 4, minus number of lone pair electron, which is 2, coming here, minus 1/2 of number of bonding electrons. So in total, we have 6 bonding electrons in that triple bond. So 1/2 times 6. You do that calculation, 4 minus 2, that's 2, and minus 3, so that's -1. You can do the same for oxygen. So that's, now we have 6 minus 2 from the lone pair, minus 3 from the bond, and that equals to +1. Or in another word, we can assign formal charge on carbon with -1, and on oxygen, that's a +1. So just as a quick side comment here, so formal charge are very useful in Lewis dot diagram just to balancing up the entire charge in your molecule. But in reality, the formal charge are not real charges. So for example, I'm a computational chemist, so I can submit the carbon monoxide into like quantum mechanics calculation and just calculate the actual charge on each atom. And our calculation would show that the oxygen is negatively charged. But that's a side note. I'm not going to test you on that. But just to keep in mind, formal charge are not real charges. They're just like placeholders to tell you how your Lewis dot diagram works. All right. So before we move on to resonance structure, I have one more topic, which is violation of the octet rule. So octet rule is super useful. It tells us lots of things, like how many numbers of covalent bond you can have. And by deriving the octet rule, you can easily draw the Lewis dot diagram. However, we might have violation of the octet rule in 3 different situations. The first one is called metal hydrides. So metal anhydrides, they just don't have enough electrons there to fulfill the octets. Like lithium hydrogen, boron hydride, they just don't have enough electrons. I'll just delete this later. So lithium hydride, in total, you only have 2 electrons. So no matter what you draw, you just never can have octets of electron on your lithium. So that's an obvious violation of the octet rule. The second one is when we're saying there can be a valence shell expansion of something that's period 3 or plus. So anything above period 2, you have a possibility of valence shell expansion, so it violates the octet rule. So using the sulfate, which is SO4 2- as an example, if you put the sulfur in the middle, this way you can minimize the formal charge by having double bonds with the oxygens. Without violating the octet rule, you will have lots of formal charge builds up. So the valence shell expansion, when we're drawing the Lewis dot diagram, it nearly only happens for phosphorus and sulfur. And also like arsenic, selenium. So group 5 and group 6 elements in period 3, 4, 5, and etc. So when you're having those atoms as your center atom to draw the Lewis dot diagram, just pay attention, they might have violated the octet rule if you can minimize the formal charge by doing that. For this course, I'll try my best to give you a hint, like if a molecule is violating the octet rule, I'll leave a hint there to say it might have violates the octet rule. And again, when we say it violates octet rule, it means if we're counting the electrons surrounding that sulfur atom, it has more than 8 electrons. That's all what we're saying. All right. The last one, when we're saying violating octet rule, is when you have odd electrons. Again, it's similar to your first example. You have odd electrons. You just don't have that number of electrons, so you can pair everything up. So NO, for example, it is a single radical. If you calculate the total number of electrons available in NO, so that's 5 plus 6, that's 11. And naturally, it is you will have one leftover free radical or this unpaired electrons available. Yes? Right, so going back to the valence shell expansion, what we're saying here is when the sulfur or phosphorus or any of those elements act as a center atom, if we're not violating the octet rule, you can imagine we end up with a Lewis dot diagram that's like this, with an excessive number of formal charge build up, which is not good when we're talking about the Lewis dot diagram drawing. So the solution here is we know that sulfur may have take more than 8 electrons surrounding it. So by making double bonds with 2 of the oxygen, we're minimizing the formal charge, and therefore this is the more valid Lewis dot diagram. Yes, so the way to think about it is the left one is resemble the reality more closely. We haven't talked about resonance structure yet, but if you measure the SO distance in the real life, it's not a pure single bond. It's shorter than your single sulfur-oxygen bonds. So the right way to put it is, yes, this structure resembles the actual chemical bonding in reality a little bit better than the one showing on the right. All right, so that's the Lewis dot diagram. I left some practice problem on the lecture note, so you can go ahead and try it yourself. I mean, the answer key is in the annotated note. And I forgot to delete it on my blank note as well. But feel free to practice it, and you can find ample practice for Lewis dot diagram in both your next week discussion session and any of the online resources you would like to use. All right. So moving on to our last topic of today, which is resonance structure. Resonance structures are super important in organic chemistry. We'll be using resonance structure a lot. So let's just spend some time just looking at resonance structures and just draw them. And look at the rules of resonance structures and do some practice drawing together. So first question, what is resonance structure? When we're saying resonance structure, what we're saying is there exists multiple equivalent Lewis dot diagrams for certain molecules. If we use NO3- as an example, and we do the octet rule. So 1/2 times 4 times 8 minus 5 from nitrogen, 6 times 3 from oxygen, and 1 from that charge. We end up with a total of 4 covalent bonds. So if we put the most electron positive atom, which is nitrogen, in the center, and we put the oxygen on the side, so now we have a question. So for this drawing, where do we put that double bond of the oxygen? Apparently, we have 3 different ways to do it. So that's one of the ways. And here. Right, so that's one of the ways you can put that double bond. And you can put it on the top. And on the left. So I'm just assigning the formal charges like I know it. If you're not familiar with how to do it, just try it yourself, use that equation, and see how that's working. So what we're having are 3 equivalent or equally valid Lewis dot diagram that's describing the chemical bond in NO3. In here, again, what we're saying is 3 different resonance structure. We use this double-headed arrow to connect these resonance structure just to indicate we have 3 valid Lewis dot diagram in order to describe the chemical bond in this molecule NO3 minus nitrite minus. One of the common misunderstanding when we talk about resonance structure, it's like in the NO3 minus, in this entire molecule, it does not oscillate between different resonance structure. Rather, when we're talking about resonance structure, the reality is more like an average of all 3 structures built up together. So here are some numbers. When we look at the chemical bond, we can actually measure the bond length of NO using spectroscopy method. What our observation is all 3 NO bonds will roughly equal to 1.24 angstrom. So angstrom, that's a unit that's 10 to the negative 10 meter. So this 1.24 is in between a pure double bond and a pure single bond. So in reality, the NO bond is something in between. It is not a pure double bond. It's not a pure single bond. All of them have some double bond character and some single bond character. And the resonance structure is describing it by saying, hey, we have 3 different Lewis dot diagrams that are equally valid. So that's the first rule. It's a common misunderstanding I just like to emphasize. Resonance structure, you just draw different Lewis dot diagram, and then they don't oscillate between each other. The reality is more like an average of all the Lewis dot diagram together. That's the first piece of information. Second piece of information, how do we draw the resonance structure, or how do we know if 2 structures are resonance? So one thing to keep in mind is that molecular skeleton will not change when we're drawing the Lewis dot diagram for this resonance structure. So I'm showing here 2 different molecules. Just quickly look at it and think about it. Are they resonance structures to each other? So even if your carbon atoms and the oxygen atoms are all stayed in place, we do have one of the hydrogen that's moving from the CH2 to the oxygen. So because hydrogen atom has moved in these 2 structures, this is not a resonance structure. This process is actually called tautomerization. You'll learn that in 14D. But these 2 are not resonance structures because you have moved the nuclei of a hydrogen. All right. Next up, we talk about the equivalent resonance structures of NO3 minus. We can also have non-equivalent resonance forms, which means you can draw different types of Lewis dot diagram. Some of them are more valid than the other. So what does that mean? Well, use the formic acid as an example. So I draw the molecular skeleton of formic acid, and you can try it yourself, but if you do the octet rule, you'll figure out there is a double bond in the formic acid. One of the ways is we can imagine this carbon here doesn't have octets of electron, and we can connect it with this oxygen with a double bond, and then add the lone pair around so that all atoms have octets of electron. All right, so that's the first step. Every time you draw the Lewis dot diagram with period 2 elements only, just check the octet rule. That's always step 1. Alternatively, you can also make this double bond between the carbon and the alcohol oxygen, which is the OH oxygen. But by doing that, what it means is we'll have built up formal charges on both oxygen. So when we have these two pairs of Lewis dot diagram, what we're saying is the left structure will be our major resonance structure because it has minimized the number of formal charge on your molecule. On the right-hand side, this will be our minor Lewis dot diagram because of the formal charge buildup or formal charge separation. So that's in your formic acid as an example. Let's do one more example together. So CH2NN. Again, try it yourself, but if you do the octet rule, we figure out there exist 2 double bonds in this case, or a total of 6 covalent bonds, if you may. So one way to do it is you can have double bonds. 2 double bonds between carbon and nitrogen and nitrogen. And you add the lone pair here. So 1, 2, we need 2 lone pair on the nitrogen. We can calculate the formal charge on this nitrogen. That's one way to draw it. Potentially, you can also draw it with a triple bond between the 2 nitrogen. But now here, this one is neutral. This one has a plus charge. Carbon doesn't have octets. We need to have a lone pair. So now both structures have octets of electron. Both structures have 1 pair of formal charge separation. So here come to the second rule is when we're looking at it, the left-hand side have this negative charge on the nitrogen atom. So if we look at the electronegativity trend, nitrogen is more electron negative comparing to carbon. So the left Lewis dot diagram is more valid or more stable comparing to the right structure. And it is more valid because we have negative formal charge that's paired up with a more electron negative atom. All right. So before we conclude, we have 3 more general rules you want to know when you're drawing the resonance structure. First thing first, you always want to fulfill the octet rule, unless you have phosphorus or sulfur as your center atom. And for this course, I'll always tell you if that molecule violates the octet rule or not. Second thing, you want to minimize the formal charge. Means like the more formal charge separation will lead to less stable resonance structure. And if your formal charge matches with electronegativity, that means you want negative formal charge on more electron negative atom, positive formal charge on more electron positive atom. So these bottom 2 our justification of now you have multiple formal Lewis dot diagrams. How do we know which one of these Lewis dot diagram is my major resonance structure? We still got 5 minutes, so let's do one practice together, and then we'll take questions. So let's just think about this molecule, hypothetical molecule, CNO. So I underline C, means that our carbon is our center atom. Normally, you put the least electron negative atom as your center atom. So first thing, we do the octet rule to figure out how many covalent bonds do we have. So that's 1/2. 8 times 3, because we have 3 p block atoms, minus 4 from carbon, 5 from nitrogen, 6 from oxygen, 1 from charge. I highly recommend you do the octet rule calculation for some period of time until you get really familiar about how many covalent bonds it can make. So in total, we have 4 covalent bonds in this molecule. So if I just draw it, I'm just going to draw the skeleton first so that I can copy paste it down. Sorry if you're using a notebook, you can't copy paste. And now the question becomes, where do we put that double bond or the triple bonds? One obvious way to think about it is carbon making double bond with both end atoms. And then we can add the electrons so that it has 4 octets of electron. So after doing that, we see there is a negative charge, building a formal charge on the nitrogen, on the first structure here. The second resonance structure, you can imagine carbon making a triple bond with the nitrogen. And we have the negative charge on the oxygen. All right. Or you can have the extraordinary third resonance structure. We'll have a carbon triple bond to oxygen. And here we have a positive charge on the oxygen and a -2 on the nitrogen. Again, you can calculate these formal charge using the equation we gave. And once you're familiar with it, you sort of know if the oxygen is singly bonded to another atom, it's likely to have a -1 charge. So now we look at these 3 of them. We can rule out, we can identify our major resonance structure. So first thing, this one is going to be our minor because of the charge separation. Right, we have -2 and plus, we have too many formal charge buildup. And then comparing 1 and 2, we have 2 being our more stable one. Because in both cases, we only have 1 negative formal charge, but in our major resonance structure, we have the negative charge matches the electron negativity of oxygen. We're using lots of knowledge we learned today, right? What's the electronegativity trend, how to use the octet rule to derive number of covalent bonds, how to calculate the formal charge, and how to identify the major resonance structure. So these are the things you'll need to know, and you'll get lots of practice in your discussion worksheet as well. All right, I'll stay here for questions if you may. I have another lecture at 11, but we have 10 minutes. So you can just come by. 1 sec.